In the previous video, I mentioned that the equilibrium constant does not depend on pressure, but that it does depend on temperature. And in this video, we'll explore how the equilibrium constant depends on temperature and an equation we can use to derive, to look at that exact dependence on temperature. The equation that describes this is known as the Hoff equation, just to give you a name to go with it. But really this all comes from the Gibbs-Helmholtz equation, because if you remember the Gibbs-Helmholtz equation, d delta G over T dt at constant pressure is equal to minus delta H over T squared. This may or may not look familiar. Hopefully it looks familiar. But right, because the equilibrium constant depends on delta G, right, delta G naught is equal to minus RT natural log of Kp. We can use this to say, okay, well, if we know how delta G changes with temperature, which is the Gibbs-Helmholtz equation over here, then that tells us how Kp depends on temperature. But now let's get the actual specific relationship here. Okay, so let's start with the Gibbs-Helmholtz equation, and let's say, okay, we have, specifically we're looking at delta G naught in this case, d delta G naught over T dt at constant pressure. Okay, and that's still equal to negative delta H over T squared. But we go ahead and make this substitution, and then we can substitute, okay, delta G, we can take this equation here, divide by T, and we'll be left with minus R natural log Kp is equal to delta G naught over T. So we can make that substitution. D minus R natural log Kp dt at constant pressure is equal to minus delta H naught, since we're doing everything at standard conditions now, for our reaction divided by T squared. Okay, so we've made that substitution. Okay, now R here is a constant, so we can go ahead and pull that out of our equation here. Give myself some more room here. Okay, so we'll have minus R d log Kp dt, constant P, is equal to minus delta H naught over T squared. So then we divide by negative R, and we'll get d log Kp dt at constant P is equal to positive delta H naught over T squared. Oh, RT squared. We divided by R. Okay, and this basically here is the Van Hoff equation, but often we like to integrate this. So let's go and integrate this between two temperatures specifically, right? So if we do a definite integral from T1 to T2 on both sides, we will get that, let me give myself extra room here, the natural log of Kp at temperature 2 minus the natural log of Kp at temperature 1 is equal to this integral from T1 to T2 of delta HR over RT squared dt. And if we assume that delta H is constant over the temperature range that we're considering, much like we did for the Clausius-Clapeyron equation, we can get an expression that looks like this. Natural log of K, and combining the natural logs on the left-hand side of the equation, natural log of Kp at T2 divided by Kp at T1. So these are not being multiplied by the temperatures. This is saying this is Kp at the temperature 2, Kp at temperature 1 is equal to negative delta H naught over R. The negative sign comes from the fact that we're integrating 1 over T squared, so there's a negative that pops up there, divided by 1 over T2 minus 1 over T1. So we get an equation that looks very similar to the Clausius-Clapeyron equation, but now it's relating equilibrium constants instead of vapor pressures to temperatures. So if we know delta H naught for our reaction, then we can find, if we know Kp at one temperature, we can find Kp at a different temperature. One other thing we can do with this is that we can if we are able to measure multiple equilibrium constants as a function of temperature, we can plot the natural log of the equilibrium constant that we measure versus 1 over the temperature. We'll get a straight line that can tell us negative delta H over R. Right, so that the line that goes with this slope would be equal to negative delta H naught over R. So this is yet another way to find enthalpies. In this case, it's an enthalpy of reaction instead of an enthalpy of, say, vaporization or whatever else. But yeah, so this is another equation that we can derive via the Gibbs-Helmholtz equation to show how equilibrium constants depend on temperature, and if we know some of these values, if we know delta H, we can find a new equilibrium constant at a different temperature, or if we can measure a bunch of equilibrium constants as a function of temperature, we can find delta H.